We're continuing our lectures on X-ray diffraction, and what I have here is an early diffraction pattern. And for the most part, with the exception of single crystal diffraction, diffractometers give you a spectra, so you have to figure things out from looking at a line on a screen. But the early days of diffraction, namely Lau diffraction by a scientist with the last name of Lau, and we'll talk about this person later, generated diffraction patterns that look very much like what you see on TEMs. So X-ray diffractometry looks a lot like electron diffraction if you look at it from a pattern point of view. And so what we have here is we have a diffracted beam, and we have we have the center beam is the transmitted beam, excuse me, dope. And the other beams are the diffracted beams, and these spots are patterns, and depending on the crystal structure and the orientation of your crystal, you will have a different pattern. And kind of learning how to interpret these orientations kind of becomes a good art. We'll talk a lot more about pattern-based diffractometry when we talk about transmission electron microscopy. But I kind of wanted just to throw this out here where just to show you all that the earlier forms of X-ray diffraction were exclusively pattern-based. We didn't have, our society didn't have the technology to create a spectra from an incoming photon beam, basically. Right now we're going to talk about absorption and transmittance, and we're going to talk about the attenuation of X-rays, and this becomes pertinent particularly when you're talking about X-ray shielding, and if you're also doing pass-through filters. And so we'll talk about this in great length. The di dx, the change in intensity over the change in distance, is equal to negative mu times the distance, times the intensity. So negative mu times the intensity. So the amount of attenuation a beam will encounter as it goes through a substance of thickness x, we can express this in terms of negative mu times I, which is the intensity. And mu is the linear absorption coefficient. And we'll talk about linear absorption coefficient in pretty good detail, and its related parameter, the mass absorption coefficient, which is basically mu divided by density of a material. And linear absorption coefficient is a material constant, but it's only constant based on the radiation that it's being hit with. So for a given radiation, you have a given mu, or mu over rho, which is a linear absorption coefficient over the density. To kind of talk about this a little bit more, we'll kind of look at an application that I was involved in a few years back, and it had to do with CubeSat. And the CubeSat program is a kind of a small base satellite, and the idea here is you can put a bunch of satellites in space with the same payload as roughly a big satellite. You can put out hundreds of satellites. Okay, so I'll just kind of leave that there. They've done 3D printing of using stereolithography and putting in electronics. This actually went into a CubeSat. Made in Space is a company that you all may have heard of, who kind of pioneered making a fused filament fabrication printer that went on the International Space Station. So this was actually printed on the International Space Station or in space. And the CubeSat program is actually pretty neat. And we were involved in a project at one point in time where we were trying to prove that you could make an all-printed CubeSat in space. So you have 3D printers, fused filament fabrication printers on the space station. You just need better materials. And one of the materials that we were interested in looking at was actually radiation shielding. So that's actually pertinent to this talk that I'm giving right now. So if you look, and it's not just space-based applications, it's radiation shielding for any application, but we had put out a paper that kind of talked about this, and it's directly pertinent to the subject matter that we have here for X-ray diffraction. And so we have the Beer-Lambert law, And the Beer-Lambert law tells us that the intensity of your X-ray after it is passed through a material, in this case a shield, is going to be equal to the initial intensity times the exponent of mu over rho times rho x. Okay, so mu is the linear absorption coefficient, rho is the density of the material, and that's again the density of the material. And so this is a convention thing, and we'll talk about it a little bit later. What we were doing was we were dealing with thermoplastic based printers, and so we wanted to make a tunable radiation shielding. And so if you want to calculate how well your tunable shielding is going to perform, you have to get a mass absorption coefficient for your mixture. So mu over rho for M mixture equals the mass fraction of your first substance plus the mass fraction of your second substance multiplied by their respective mass absorption coefficients. Okay, so in this case we were doing tungsten and polycarbonate. You can get the mass absorption coefficient of tungsten and polycarbonate, and whatever percentage you're using of each, you just kind of plug in chug. This is kind of an important thing to think about, the density. Okay, so if I have a mixture of iron and carbon, I put it in a bag and then somehow, make some sort of shield out of it. I glue it together or something with some sort of binder, with the amount being somewhat inconsequential. You can calculate your nominal density based on another rule of mixture type of equation. However, if I make cementite, it's not going to have the same density. Okay, so this is only working if I have, I guess, more of an amalgam versus an alloy. If it's a true mixture versus I made a different chemical compound, that's where these equations hold true. And these are rule of mixtures types of equations. Law of averages would be volume fraction, rule of mixtures, mass fraction. So you don't want to forget that. And then here's some results, and kind of put the citation before I put it in the picture. But this is, we kind of talked about it in different articles, so I'll show kind of the results of this stuff from two different articles. And so percent X-ray transmitted. So polycarbonate actually has a pretty good propensity to block X-rays on its own. And so we were only getting 9% X-rays transferred through with just polycarbonate. The shields were actually 1 centimeter, so it's actually kind of cool for this specific radiation source. Okay, when we added 1% by weight tungsten going all the way up to 5, you can see a pretty good decrease in the amount of X-ray radiation that went through. And then here's some examples. These are actually IZOD impact tests that we did for this study. So this is pure polycarbonate loaded with 1% tungsten going all the way to 5% tungsten. And you can see the difference in just the color that occurred by loading more and more tungsten. And it was pretty cool because for a really, really low weight percent, we were able to block out a reasonably high amount of X radiation according to our results. This is another graph, and they changed the X-ray energy. And one thing that you want to kind of realize is that your X radiation or your X-ray shielding, your mass absorption coefficients will change depending on the energy of your X-rays. The X radiation, I'm kind of asking you to think about this, kind of bring things that we talked about in the previous lecture with this lecture. So the shielding ability goes down as the X-ray energy goes up, and I don't know why I put a question mark there. What do you think this means in terms of wavelength? Okay, well, as the wavelength gets shorter, the energy goes up. Okay, so you have to kind of think of things in terms of that. So you'll still get some good shielding. The X-ray energy, the wavelength is actually shorter here. So think about that. Always remember E equals HC over lambda. And anyway, it was pretty cool. So the point of this graph was we were looking at attenuation factor and as opposed to percent X-ray transmitted. And I'll kind of show you the differences that and the way you kind of want to think about how to use these equations on the next slide. But the line was our model that we used, which was basically based on Beer's law, and the points that we actually measured matched up pretty well with the model, so that was actually pretty good. That's what you want to see if you're an experimentalist working with a modeler anyway. So anyway, I'm going to go on to the next slide. We'll talk a little bit about attenuation factor versus percent X-rays transmitted. So if we look at the same graph, okay, I just changed the axes. I made it look a little prettier here, but I changed the y-axis on either one. So this was the kind of the data we published, and we were publishing attenuation factor. So attenuation factor is Ix over I naught, which we saw before. And we saw that negative mu intensity equals this, but the attenuation factor is also equal, according to Beer's law, the E times the mass absorption coefficient times the density times X. And so this is more practical because you can calculate the thickness, okay? The other way was kind of more of like a derivative kind of looking thing. The amount transmitted, okay, is Ix. And so this is expressed as a percent. So more X-rays are transmitted at higher energies. And sometimes I find it easier to look at the data in terms of amount transmitted versus attenuation factor. It depends on what kind of day I'm having, actually, I'll be honest with you. But anyway, I just wanted to kind of cover that. So always pay attention to the what's being asked and how the data is presented and what kind of language you're using. Okay, so amount transmitted would be Ix. If they report attenuation factor, it's Ix over I naught. And we can go over a problem here very shortly. All right, mass absorption coefficients. I've posted a handout on Blackboard giving some tabularized mass absorption coefficients. Sometimes this data is actually kind of hard to find, but I found another database of mass absorption coefficients that I'm happy to show you, and I'll show you in this lecture. It's a parameter that characterizes a given material's ability to absorb X-rays. It's essentially the linear absorption coefficient divided by the density, and we kind of talked about this already. If you have a mixture, mass absorption coefficients can be calculated from the rule of mixtures. Again, if you've made a new chemical compound, that new chemical compound will not have the same density, and it will actually even have different mass absorption parameters or linear absorption parameters. And generally, the linear absorption coefficient / mass absorption coefficient for a chemical compound is also tabulated in its own database. The tables I'm providing on Blackboard are strictly elemental based, but I'll show you another source for this type of data. So here's an example. I'm sorry, it's kind of bad. I got it out of an old book, but it's a table mass absorption coefficients, and I kind of cut it off. This is just showing an example. We have this for all of the elements on the periodic table, I believe, or most of the elements on the periodic table. I guess we don't have some for some that don't really exist and some that don't exist in standard room temperatures. But the mass absorption coefficient for a material will change depending on the source radiation. And so this is this column here is the absorber, and I've cut off a few, but we have aluminum, which is a good metal to use. We also get the density. So linear absorption coefficient divided by the density. This is tabulated by a convention, and historically you could only find tables of mass absorption coefficients. But I have another source I'll show you here in a bit. And so this is the different X-ray source. Okay, so molybdenum, copper, cobalt, chromium. This is, if you look at the sources, the author of this table was only really caring about X-ray diffractometry because these are pretty common X-ray diffractometer sources, copper and cobalt being the most common. And if you look at aluminum, so aluminum for copper K alpha, the mass absorption coefficient is 50.23. For K beta, it's less. Aluminum, it's even higher for cobalt. So aluminum is actually a pretty good shield for cobalt K alpha anyway, and it's super high for chromium. But see, it's not always the case. So the numbers vary, and sometimes they vary by quite a bit between the X-ray source. And sometimes you can see differences in orders of magnitude. So let's look sulfur, which I don't know if I'd want to make a shield out of sulfur. Copper K beta 68. But if you look at chromium, it's 281.9. So sulfur actually absorbs chromium K alpha very, very well. Again, Beer-Lambert law, if you look at how the equations actually operate, density cancels out for Beer-Lambert law, so you're really only caring about the linear absorption coefficient, but you have to use this flavor of an equation because the data is given to you in terms of mu over rho. If you have the linear absorption coefficient, your Beer-Lambert law changes, right? So if you have the linear absorption coefficient, which is strictly mu, and the units of mu in this case are centimeters to the -1, you don't have to worry about density. And the question is, well, where do I get this data? Because sometimes this data is actually hard to find. NIST, the National Institute of Standards and Technology, has made this great database. And I'm going to show you kind of an example of me using it. And hold on. There we go. So you can pick whatever material you want. In this case, I'm picking iron. I didn't turn the volume off, but that's okay. But you also get linear coefficient, and you can pick the range, and you can get the data, and you can play around with this. You have the link, so play around with it if you like. And so it gives you a whole range of data. You get a graph. You also get edge absorptions, which we'll talk about later. But this actually gives you edge absorptions for a wide range of orbitals, right? So we have K, we have the multiple M's, and then we have the multiple L's as well. And sometimes L and M overlap in terms of energies and stuff like that, absorption and edge absorptions. And we'll talk about the absorption edge. But first, let us work out a problem. Right, so I have a problem we're going to work through, and I'll read it along with you. So say you have an X-ray generator, and you want to block out 99% of the X-rays, so you want to shield yourself pretty well. And so let me use my highlighter here. So 99% of the X-rays. You have some iron, and you want to make a shield out of this iron. And how thick should your sample be? And so we're going to use the Beer-Lambert law. Oops, got a little. It's supposed to be mu over density. Mu over density, density x. So we're going to solve for x. So this is how much is passing through. What the original was, E mu over P, and I wrote it very sloppily. I can do a little better than that sometimes. Then rho x. And so I to the x, that's how much is going to pass through. I naught e to the negative mu over rho times rho x, and we're going to solve for x. And kind of highlight that. That's what we're solving for. And if you want to kind of draw it out, we have this shield we're trying to make. We have these X-rays kind of coming through. It's supposed to be an arrowhead. Again, I can do better than that. And don't get confused with X-rays and distance x. And we're going to solve for the distance x. So we're going to see how thick we want this to be. So some things you want to look at. So you want to pay attention to the terminology. And so we want to block out 99% of the X-rays, which means only 1% is going to pass through. So Ix, we already know it's going to be 1%. I naught would be 100% passing through, and this is only 1% passing through. You can convert this to a number, and then I naught kind of goes away, and so Ix you can say, and then you can say I naught is equal to 1. So you can rewrite your equation, and in terms of just the numbers we've just substituted Ix and I naught for. And so that's 1, so we can just say e to the negative mu over rho times density times x. So we're going to have to solve for x. So we have an exponent. We know we need a natural log for that. So let's plug in the numbers before we plug in chug. The numbers we want to use, come off this, I just made a big boo-boo. Boom, pasted my highlighting. The numbers we want come off of a table. And the table we want is this table that I tried to put in, but I put in highlighting by accident. And let's kind of scroll it down. We can make it bigger. And I covered up my equation here. Boom. And I think this is big enough. We can also zoom in. So we have our different values we want. So our absorber, in this case, our absorber is going to be iron. And we're dealing with cobalt, K alpha, if we go back and look. So cobalt, K alpha. So these are the critical parameters we want to look at here on our table. Sometimes on tests, people get the absorber and the X-ray source mixed up. So just to be kind of courteous, I don't use cobalt as an absorber on test problems because that causes trouble for people. They actually get the concept, but they made a mistake. Maybe they were nervous or whatnot. So we're dealing with iron. And so iron, if I follow along, is 56.25. So that's the value for iron. I kind of goofed. I covered it up with my pen. Here, let me use a different highlighter to make it a little more clear for you all. And iron 56.25. So iron 56.25. Don't use the cobalt number. So 56.25 is our mu over rho. Density is nicely given to us, and a lot of people have this memorized. It's a common metal used by metallurgists to make steel and the like. So we can rewrite our equation. So 0.01 equals 56.25, and we can use, oops, you know I made this sloppy, and I apologize. And I actually had forgotten the exponent. Dope. So e to the negative 56.25. This is centimeters squared per gram. Always remember the units. The density is 7.87 grams per centimeters cubed. I'm making this a little sloppy. Let me try a little harder. Sorry about this, y'all. All right, 7.87 grams times x. And x is going to be in centimeters. So x has to be in centimeters for the units to cancel out. That's why I always write out the units. Because this would be dimensionless, right? 0.01 is rads per rad if we look at the other slides we've done. Anywho, or unit per unit. Anyway, this has to be dimensionless. Hopefully you can read my sloppy writing. It's a little bit hard on a tablet. All right, so ln 0.01 equals ln e, and then let me write it again just to make it a little neater. I'm going to only put the numbers just to save space. (7.87x). Okay. So ln 0.01. I have a calculator somewhere. I can't do that in my head. And maybe somebody borrowed it from my office. But let me fire it up. Sorry about that. 7.87, and follow along. I implore you to. Oops, ln 0.01. Dope. So I got negative 4.6. I'm going to round up 4.61. And this equals to this ln and the e are going to cancel out. So it's simply 50 or negative 56.25 times 7.87. And I got 442 point, we'll round that up, 69 x, and we know x is going to be in centimeters, and it's a negative, and so we want to divide this by 4.61. All right, so we've worked out a problem with mass absorption coefficient, and now we're going to talk about the absorption edge. And the absorption edge is another material property, and it's dependent on the radiation hitting it. And if I read my own slides, the critical wavelength that has the energy to ionize an atom or basically knock a given electron out of its shell. Okay, and you saw on this NIST slide that their absorption edges can occur for different specific radiations, and I could probably figure out which one this is. I think this is K for iron and aluminum, but the absorption edge is very interesting when you're developing an X-ray diffraction system. So if you remember, you want to have monochromatic X-rays to perform X-ray diffraction, because if you're performing diffraction with multiple wavelengths, you'll get a lot of peaks and it will be impossible to interpret your data. Okay, so you have to know what radiation you're using. And the absorption edge kind of works like this. I'm going to explain it on this slide, then I kind of explain it again on another slide using a figure from Cullity. But let me get my laser pointer. So for iron, which is the black line, and aluminum, which is the red line, they have different absorption edges, and this is, I believe this is K. Okay, it didn't specify, but I'm guessing just by the energies it's K. So your mass absorption coefficient, so it's going up, going up, going up, going up as your wavelength increases, right? So if my wavelength increases, the energy is actually getting lower, so I'm able to absorb more energy. But here we have this kind of interesting phenomena where it just sharply dives. It takes a nosedive. And what's happening here is you're ionizing an electron. Okay, so the energy, if you remember, electrons are at given energy levels, okay? And if they have an energy, they also have a wavelength. This wavelength is also going to have an energy. So when the energy of your incoming X-ray matches the energy of your electron, or if you want to think of it in terms of the wavelength, if the wavelength of your incoming X-ray matches the wavelength of that electron, they're going to do a little dance, basically, okay? And it's going to, boom, knock that electron out. If it's not there, okay, it's going to either be too low for the electron to care about, or it's going to be too high for the electron to care about, and the X-ray is going to be looking for higher energy electrons. So when the energy or wavelength of the X-ray is matching the energy or wavelength of the electron, they're going to collide, basically, and that electron is going to be ionized. Now what that means is you've knocked this electron out of the way, so it's kind of like the battle droids going through the Gungan shields in episode 1, if you will. That X-ray is going to be able to pass through pretty easily, okay? And so what happens now is you have this point where the X-rays are passing through, so it's not a good absorber anymore. And then it takes a little while for it to recover its behavior in terms of wavelength. And we see that aluminum and iron have different edge absorptions, and I'm guessing this is K. At the very least, it's the same radiation that's being talked about, I believe. Anyway, different absorption edges, okay? If we look at it, and here we are, they're the little cusps. If we look at it from kind of a different point of view, so this is talking about nickel, and nickel is important to copper radiation, and I'll show you why in a bit. But here's the critical energy for the wavelength of an electron from nickel, and we have this spike, and so this is the absorption edge of nickel. And so the absorption edge of nickel occurs a little bit below 1.5. And the energy of the X-ray matches that of the electron. So think levels. Here, the material is absorbing a lot. After you get this, hit this absorption edge, the absorbance decreases. Well, why do we even care about this, man? Why am I trying to wrap my mind around this? Well, you can use it as a filter. And for whatever reason, I put it in terms of nanometers, but 1.48 is the nickel edge. 1.54 is K alpha, and 1.38, and I'm talking angstroms, but I'm showing nanometers, I'm sorry. So 0.138 nanometers, 0.154 nanometers, and the nickel edge is right in between. Well, if I overlay what we see for the absorption edge, nickel had a really, really good propensity to absorb radiation right here at the K beta area. But it was substantially decreased because of where the absorption edge lies, so K alpha can pass through. And so what we're doing is we're essentially creating a K beta filter. So we're filtering out the K beta, and we're only letting the K alpha pass through. And that's important because we want our diffracting beam to be monochromatic. We can't have polychromatic beams creating diffraction because you'd have peaks all over the place or dots all over the place, and you wouldn't be able to make sense of what was what. Okay, so keep that in mind. A drawback to using a nickel filter or any metallic filter or a so-called pass-through filter is that you also attenuate the radiation you care about. So if you look, the intensity of K alpha is decreased with and without the filter. So this is no filter, this is with the filter. I was backwards with my mouse pointing, I apologize. But no filter, K alpha is more intense. But the benefit of using the filter is you've gotten rid of K beta, so you'll actually have less peaks to confuse you. Here's different filter materials, and all these materials have the absorption edge lying between the K alpha and K beta of your target. So for molybdenum, zirconium is a good filter. For copper, we've talked extensively about nickel. For cobalt, iron is a good filter. For iron, okay, manganese is a good filter, and for chromium, vanadium is a good filter. So it's pretty cool. It actually gives you, it's funny, it gives it to you in terms of inches. So anyway, again, from B.D. Cullity, written in the 50s, seminal work on X-ray diffractometry. Here is the absorption edge. So I'm going to give you this table as well, and it's pretty much every element or most of the elements on the periodic table, giving you their K alpha 2, K alpha 1, and K beta, and we have the weighted average, which again, the weighted average is in terms or in favor of K alpha. So it's 2 times K alpha plus K alpha 2 divided by 3. That's the weighted average. You don't get K beta doublets, which is kind of interesting, but we also get the absorption edge for our elements here. And note, we don't have the weighted average for everything. So not every material gives a discernible K alpha doublet. So if you look at these numbers, it's not really worth it to try to weight it out. I think it's funny because Brandon and Kaplan, they borrow Cullity's graph almost exactly. They just color it and then don't give Cullity credit. So if you go and you look, this Cullity's graph, this one here, they've repeated it here and put it in nanometers instead of angstroms. So I guess they don't get copyright infringement. But anyway, instead of using a pass-through filter, you can use a bent monochromator. And we have this on our X-ray diffractometer. Sometimes, though, K beta can bleed through, which is kind of interesting depending on what you're looking at. And I've actually seen that with a student because we recalculated some of her peaks based off of what K beta is. It was kind of an interesting thing. Only seen that once in all my years. But a bent monochromator is basically diffraction grading. And what happens is only K alpha will satisfy the Bragg condition. And so in the next lecture, we're going to talk Bragg's law up to Bazango. But the key thing you want to know about Bragg's law is diffraction will only occur for, if you have a static D spacing, diffraction is only going to occur for one wavelength. Okay, and so this is going to be oriented so you only have one angle. Okay, so it's like the monochromator on the spectrometer that was moving. In this case, it's not moving, it's static. So only K beta is going to go through. And this is on the tube side. This is a filter within the X-ray tube. Okay, and so the filter would also be on the pass-through nickel thing, would also be on the pass-through tube. So if I asked you on a quiz or a test, what's a drawback of using a metal pass-through filter such as nickel? The answer would be you also attenuate K alpha. Okay, so part B, what would an alternative to a nickel pass-through filter be? Well, a monochromator that only allows K alpha to pass through based on diffraction condition. Okay, so think of it that way. So the next lecture, we're going to talk about Bragg's law and diffraction very much. These first two lectures were kind of talking about X-rays, specifically aspects about X-rays that pertain to X-ray diffractometry, and the understanding of which you kind of need to understand what's going on with X-ray diffractometry. This is yet another good place to stop for now. So as always, I thank you for your time. Be sure and pay attention to the the worked out problem we had in this video as well. You never know when that might come up again. And have an awesome day.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.